In this video, we're going to talk about binary search trees. In the last video, we talked about a binary tree. So a binary tree is a data structure that, unlike a linked list, which only has a child, basically, so every node links to the other nodes in a horizontal fashion, a tree is a vertical structure where the node can have two or more child nodes that pop out. We do this in a vertical fashion. So a binary tree in particular has two children, a left child and a right child. And we looked at a simple example of that last time, and we were able to create a binary tree, add a left node, add a right node, put some integers there, and look how that worked. We also talked about the traversals. So the in-order traversal would put it in the order from furthest left to furthest right. And we'll talk about that more today. There was also the pre-order and post-order. Okay. So we had the problem, even if we only had a relatively small tree. So the tree we have here, it has 1, 2, 3, 4, 5 elements. Okay. But if we went to insert a new element, we've got 6 possibilities. Okay. From root, we could go left, 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 or left, left, right, or left, right. So left, 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 right, left, right, right, left, right, right, left, and right, right, right. And that's only for 3 layers or 3 levels. The more you get, the more difficult it is to know where to put things. So we want to have a way to automatically, when there's a new element, we know where to put it. We don't have to specify multiple layers of where it's going to go. We also don't have to know what the tree looks like. Okay. So we're going to do this through the idea of a binary search tree. So the binary search tree is a binary tree, but but it differs in that for any node, the left child is smaller. So the info stored in the root node, the info stored in the left node is less than the root node, and those to the right are greater than. Okay. So what I have on the screen here is not just a binary tree, it's a binary search tree. 6 is bigger than 3, and 6 is smaller than 8. For this node, 2 is smaller than 3, and there's nothing bigger than 3 from 3. We don't care about this stuff. And then from 8, there's nothing less than, but 9 is greater. And from 9, we have nothing on either way. Okay. So what this does for us, we know where to put things. So let's say we're going to put a 7 here. Okay. We start at the root. Okay. The root's not empty, so we have to worry about that. Not empty. So we have to see, is 6 greater than or less than the 7 we're trying to do? Okay. So 6 is less than. Okay. Which means we're going to go to the right. Okay. Everything that's greater, the info. So let's put it this way. The info we're storing is greater than 6, we go to the right. Now we're at 8. Okay. And we have to make sure that this isn't, if this were blank, if this were a null pointer, we would just put the 7 here, but it's not. We've got an 8. Start again. Is the value here, is the value we're trying to store greater than or less than 8? It's less than, so we're going to put it over here. It turns out this one is vacant. There's nothing there. It's a null pointer. And that's where we would insert the 7. So the 7 will be at the right left, basically. Okay. So that would look like this. So as we add new nodes, we're always going to be able to put them in the right spot. Okay. So one of the reasons we do this, first, we know where it's at, but also it's going to make searching easier. Okay. So if this were in a random tree and we were looking for 12, we would have to do some kind of traversal and check every element until we found it. If it were found over here at the 9, we would have to go everywhere, depending on which algorithm we're doing to get to it. Okay, so that's just like a sequential search. But if we have this binary search tree, it's easier. Okay, so we go to the root node here. Is this what we're looking for? It's not. Is what we're looking for greater than or less than? It's greater. We go here. Is this what we're looking for? It's not. Is what we're looking for greater than or less than? It's greater. We go to here. Is this what we're looking for? It's not. Greater than or less than? Greater. We're going to go here. We hit a null, which means we didn't find it. So we only had to do 1, 2, 3 comparisons instead of 1, 2, 3, 4, 5, 6 for this small example. Okay. So it becomes a lot more efficient. We'll talk more about the efficiency later, but at least theoretically, it's more efficient. So here is what the formal definition from the book looks like. Okay. So a binary tree T is either empty or it has a node called the root node, and T has two sets of nodes, L sub T and R sub T, that are called the left subtree and the right subtree. Okay. The key in the root node is larger than every key in the left subtree and smaller than every key in the right subtree. And both L sub T and R sub T are themselves binary trees. Okay. So the book also gives us some operations that are typically done on the binary search tree. Okay. So we determine whether it's empty. We're going to search for a particular item. We're going to insert an item. We're going to delete an item. We're going to find the height of the tree, okay, which is how many layers there are, or what's the longest path from root to a node. Okay. We can find out the number of nodes in the tree, the number of leaves. So a leaf node is a node that has no children, no right or left child. Be able to traverse the binary tree. We've already talked about that. And be able to copy the binary tree, do a deep copy to make an actual copy of it. Okay. So the book has a class that they create for binary trees and that they extend to do binary search trees. The binary trees an abstract class. And that, I'm not going to have you type all that in this time. I will just put that out on the server, but we'll look at that in a second. I want to start with a simpler example. Okay. So let's go back over to the server here. Okay. And this is the example we were looking at before. So we've simplified this in that we're only allowing integers, so there's no typing involved. We're not doing a class. We're doing it as simple as we can. Okay. So we still have our binary tree node, which has the info, the left link, and the right link as we had before. Okay. And we're going to skip over this for the moment. And we're just going to create this. So where before we created a left and a right. Okay. There's still our pre-order. I've added in order, and we'll see why in a minute. Okay. So we're still going to do the basic idea that we're going to create the pointers to the binary tree nodes, and then we're going to set root to be a new binary tree node, and then set our initial root information. I'm then going to run this insert on 2, 52, 21, and 16. Okay. So visually, 12 is going to be at the root. 2 will go to the left of that. 52 will go to the right of that. 21 will go to the left of 52. And 16 will go, okay, I've got 12 to 52 to 21. The 16 will be to the left of that. Okay, that's what that should look like. Okay. So let's talk about this insert. Go back up to the top here and go through the code here. Okay, that's the search. We'll get there in a minute. Okay, and this is one that I typed this up myself. It's not based on anything else. I use the same nomenclature or the same names for things as the book did, but besides that, it's all new. Okay, so this is a binary search tree T we're sending along, constant on the insert item. We're sending that as a reference. Okay, I could have made this a constant, but then I would have had to make this a constant when I copy it over. Down the way here, down with T. So I just didn't copy it over. We're just using T as the root. Okay. Probably not the best, but it will get the job done. So we have nodes for current, for trail current, and for new node, which will get us going. We're going to use pointers to find where we want to insert things. I'm then creating a new node. It's a new binary tree node called new node. I'm setting the info on whatever the function takes in as a parameter. So this insert item gets set here. Okay. I'm then setting the left link and right link to null. So this is a node that's not part of the tree yet. Now I've got to figure out what to do with it. Okay. So T is our tree we're passing in. If T is equal to the null pointer, it means that T has no nodes. So I just set T equal to new node and we're done. Okay. So no issues there at all. Okay. Oh, that's why the binary tree can't be constant because we are changing it. So forget what I said before. The binary tree T has to not be a constant because we are changing it. Okay, so else. So all of the rest of this down through here is all assuming that it is not empty. Okay, so we're going to set the current pointer equal to T. T again refers to the root or the first node of our tree. Okay, So while the current is not equal to the null pointer. Okay, so once you find the null pointer, you're done looking. Okay, we're going to let the trail current equal to current. Again, when we get to null, we're going to have to insert on the one before. So just like we did in inserting in the middle of a linked list. Okay, so if the current, so whichever record we're pointing to, is equal to the item, or if it's equal to the thing we're trying to insert, okay, not doing search yet. So if the current info is equal to the insert item, then we can't have duplicates in trees. So we're going to just give them a message. We do a return. The return there, it's a void function. It's going to be fine. Okay. Else if, okay, so if it's not equal to the item we're looking for and we're inserting it, it's either bigger than or it's littler than. Okay. I tend to get myself caught up in circles sometimes on which is which, but this is correct because I've tested it. So if the current info, so what's at the node that we're on, if it's greater than the insert item, it means the insert item must be less than, therefore current is equal to current L link. So we're following the left subtree to try to insert it. Okay. If not, if it's not equal, not greater than, it must be less than. Okay. And then we go following the right link. Okay. So that's going to keep going around in this while until we get to a null pointer. Okay. When we get to a null pointer, we found the node where we need to insert. Actually, we found the node whose parent is where we need to insert the new information. Okay. So from right here, we can just check to see if the trail current info, so this is the one that got us here, if it is greater than or less than the trail current of the insert item. Okay. If it's greater than, then we're going to set the trail current left link to new node. That new node goes into the left of the node pointed to by the trail current. If not, we're going to set it as the right node. Okay. And that should insert all of our items. Okay. Without any trouble. Okay. So there's more in the test program, but let's go ahead and run this just to see what this looks like. I'm adding some things here. So I'm going to go ahead and compile that. Again, I'm being lazy and doing the a.out. You shouldn't do that. Okay. And we see here that I've done a pre-order traversal down here just because that makes it easier to see that our tree is working correctly. So on a binary search tree that's in order, the very first item that the in order, that's why it's called in order, it's going to be the one furthest to the left, which is the smallest item in the tree. So if these are in order, which they are, even though I did not insert them in order, then we know that our binary search tree is being created correctly. Okay. So that's the idea behind that. So the search we looked at before on the picture, so we can also code up the search on our simple example. Okay. The search here, again, is going to take tree link. Okay, it's going to take a search item this time. Search item's a constant, it's not going to change. We have this Boolean we're going to set up found equal to false initially. We're again going to have a current and our trail current, which we're setting initially to the null pointer. Okay. Then just for convenience, we don't have to do this, but just to keep it looking like we've done before, we're going to set current being equal to t, which is the address of the tree coming in. So it's the root of the tree. Okay. So here we're going to say, we're going to check to see if the tree is empty. So if current is equal to the null pointer, we're going to return false. If there are no nodes, then our search item can't be there. Okay. I'm then going to go through a loop while it's not found. So once it's found, we can stop. We're going to check the current node, wherever we're at. It's the first time through, it'll check the root node, and to see if the current info is equal to the search item. If we find it, we return true. Okay. If not, we're going to see if the search item is bigger, if the current item is bigger than the search item, which means we need to go down the left link. We're checking here to see that if it's equal to null, it's equal to the null pointer, then we're going to return false so that we've ran into the end. But if it's not equal to the null pointer, we're going to go ahead and move to the left link. That'll get us out of the if loop, back to the while again, and we'll try again. Okay. And then we have here our else, the same idea. If it's not less than, it's going to be greater than. We've already checked to see if it's equal, and it's not. Okay. So we're going to do it here. And we're going to let current equal the current right link or return false. Okay. That brings us back around to the while again. And eventually, either it will find it here, or we'll end up with a null pointer that we try to get to. Okay. So that's the basic idea behind the search. Okay. And then just to show you here on the in order, instead of being visit left right, it's left visit right. Okay, so I've got here just if we're sending in the search tree, if the L link is not equal to the null pointer, okay, we're going to move to the left. And then our visit is just we're going to print out the info for that. And if not left, we're going to go to, so if it's if the R length is not equal to the null pointer, we're going to go to the right. Okay. So we do left, we do print, we do right. We're going to keep doing there. Okay. So our tree here, we're just creating our initial tree, which has its value that we're setting. Again, I'm not creating a class, so there's no constructor or any of that stuff. I'm inserting the 2, the 52, the 21, the 16. I'm then doing the pre-order traversal, which we had before. Then I'm doing the in-order traversal. And then I'm just testing the search, searching for a couple of different things and printing out that the 52 should not be in the list, but the 52 is, sorry, and 53 is not. Okay, so that's the basic idea behind that. So let's switch back to the text document here. Okay, see where we were. It wants to jump around on me. That's all the same code we just looked at. Okay, so the next thing after inserting is searching is deleting. Deleting can be sticky. So the idea in general of deleting is not too bad. I mean, we can pretty easily find the node we're looking for with a search. Okay. Removing it's not usually a problem. The problem is when we're done removing an element, it still has to be a binary search tree, which means we sometimes have to work things around. Okay. So I've got this example here of a tree that's from the book. It's figure 19.9. Okay. So when we're looking at this, there are 4 cases we have to consider. The first case is that the node to be deleted has no left or right child. Okay. It's a leaf node. So that's 45 in this case. That's the simplest of cases. Okay. It could be that it has no left subtree, which is like 40 here. Left subtree is empty. Okay. It could be that it has no right subtree. Okay. 80 is an example of that. Here has no right subtree. Or it could be that it has that there's no empty at all. Okay, we've got 2 non-empty subtrees. Okay, so like 50. So 50 has 2 children. Okay, so in the first case of 45, easy to get rid of, not a problem. Okay, in the case of 40, where there's no left tree, okay, we know that 40 has to be bigger than 35. There's nothing here to worry about, so we can just move the 48 up to here and things are going to be fine. Okay, that's what we'll have to do. Okay, on the 80, a similar issue. The 75 is less than the 80. Okay, the 75 is greater than the 70. Okay, so since there's no tree here, I can just move this back up to here and everything else will still be fine. Okay, the trouble comes in when we have something that has both. Case 4 is a trouble here. You know, I can't just, I have to figure out, am I going to move 30 up? Am I going to move 53 up? Okay, that's where things get a little more complicated. So this just goes through, this is from the book, more or less. It goes through the things we want to do. There's not an issue here. But again, the 50 is the problem. Okay, so what we're going to do here is we're going to reduce it to either case 2 or case 3. Okay, So we're going to look for the immediate predecessor of 50, which in this case is 48. Okay, so we're at 50. How does it get the immediate predecessor? That's really, have they switched info on us? Okay. Okay, it's going to the left child of 50 and then locating the rightmost node of the left subtree of 50. Okay. We've got 50. Oh, I guess from here, from this 30, they're finding the biggest thing that's in that list. Okay, that's where the 48 comes from. Okay, that's down here. Because the binary search tree is finite, we will eventually arrive at the node that has no right subtree, which makes it the biggest in that part of the tree. Then we're going to swap the node, in the info in the node to be deleted with the info of the immediate predecessor. So we're going to swap the 48 to 50. Okay. When we swap the 48 up with the 50, okay, then we're going to be left with, we're basically moving 50 off to the side. Okay. And it means that the rest of this left subtree, it's all going to be less than the 48. 48 is the biggest in this area. This goes up to here. This is still going to be bigger than that. Okay. We then reduce it to the case where there's no right subtree for the 50 because the 50 is going to be down here. We can now just move this up and we'll be fine. Okay. So that's the way that's going to work. Okay. So I didn't implement that. That's going to be a little more complicated. Okay. So I do want to look briefly. I'm afraid this video is getting long already, but sometimes you need to. I want to look at the code that the book has done for these various things here. They again start with this abstract class on binary trees. So this is more thorough than the one that I did. I did one just to give us an example of what's going on. Okay. So again, this is from the book and I will make it available to you so you don't have to type all this in yourself. Okay. So we have the struct as we have before. The difference being that we're using a template here. So this can be answer doubles or even custom types like a class objects that you create. Okay. We didn't have a class for this. The class will have to have a constructor. What we start with, because we're holding these, the links here are memory things. We have to do all that stuff we have to do before. We have to have a copy constructor. We have to have a delete destructor and a constructor, and we have to have we have to redo or overload the assignment operator. So that's showing the overloading the assignment operator. This is the thing the book said we should have that my simple example didn't. The is empty. Okay. We have the traversals, the in order. There are two traversal functions here. Okay. One we just call, and then one which is going to be a helper function as we're going through and doing the traversals. Okay. So all of the traversals have that two-part function for us. Okay. There's a tree height function, there's a tree node count, tree leaf count, and destroy tree. Okay, there's our copy constructor, default constructor, and the destructor. Okay. And we have protected data here on the root, and we have the private things. We have our copy tree function, our destroy, the in order, pre-order, and post-order are private. They get called from the outward facing functions, which have a different parameter but the same name. Okay. And then we also have a height, a max, a node count, a leaf count. Okay. It's then going to go through and define all those. Okay. So one thing we don't see here, so I guess this is an abstract function in a way, but it's not the typical way. We have no abstract functions inside of this, but the class can't be used because there's no insert or delete or search. Okay. So we have those basic operations there. And now when we look at the binary search tree from the book, it's going to include the binary tree. Okay. The constructor makes the binary search tree type a child of the binary tree type. Okay. We pass along the element type because it's templated. And what we're adding here is a search, an insert, a delete node. Okay. Now note that on all of these functions, I don't have to send along the tree because they're in a class with the tree. So that avoids some of the problems that I had on my example. And then we finally have a delete from tree. And the book it divides the delete functionality from the finding the node to delete. Okay, so that's something to be aware of when you're looking at this. Okay. And then this is going to go through. This code looks very similar to the code that I have, but it's using the internal, it's part of a class, so it can just use that data directly. Okay. And all that stuff is going to be there. Okay. And you should look through this and you'll be using that to make, to do homework problems and potentially expanding that out. Okay. So let's go back over to our other document. So we talked before, it's this function here. That's still a search. Okay. So again, one of the reasons we do this is that it makes searches perform theoretically at the log2 of n, which means it's as fast as theoretically possible. Okay. But that's only true in a balanced tree. So a balanced tree has where each half of the tree, given any node, has approximately the same number of nodes. They got to be pretty close. Okay. So if you have a balanced tree, then at every time you search, so if we're in this tree up here, then if we're searching for a 75, from here we can eliminate, and this is not a balanced tree, but the more balanced it is, the more you eliminate every time that you go through. Okay. But trees don't have to look like that. In particular, if you enter numbers sequentially. So in this case, we've got a tree, we enter a 1, a 2, a 3, a 4, and a 5. Into our binary search tree, we get this tree. Okay. The 1, the 2 goes to the right of that, the 3 goes to the right of that, the 4 goes to the right of that, the 5 goes here. Okay. The worst case search for this is the same as sequential, right? It's going to be a big O of n, and that you have to go all the way through all the records to get to it. Okay. So this is a super not balanced tree. Okay. So programmers have developed some ways to have self-balancing trees. And it takes a little more processing up front to keep them balanced, but it leads to much greater time efficiencies when it comes to doing searches. Okay. So we'll look at that in the next video. In particular, we're going to look at something called an AVL tree. So I did want to mention just at the end here that the search function and the insert function are not recursive. Okay, so the reason they're not recursive is that, remember, recursive can be difficult when we're trying to fit something into a memory space. So if you had a really big binary tree, remember one of the advantages of a binary tree like a linked list is that they're all connected to memory. They're using just their own memory. They're not taking up a lot that they don't need. They're efficient in that way. But if we had to do a search through a whole bunch of the tree with a recursive call every time, then it would quickly overwhelm the memory resources of your system. So that's why we don't do that. Okay. So that's it for today. So the binary, or for this video, the binary search trees are going to be in addition to a binary tree. And we're going to enforce that rule that everything to the left of a node is smaller, everything to the right of the node is bigger. We have no duplicates. This allows us to do searches more efficiently, again, assuming we have a balanced tree. Okay. But in any case, it allows us to algorithmically know where to place a new item without having to say go left, right, left, 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 right, left, right, left, right, and all that. Okay. So this works out better. And again, in my simple code, I went ahead and added the in order because on a binary search tree, the in order should be in sequential order, okay, or in normal order, with the smallest to the biggest, okay? So there's at least one more video on trees to come, maybe two, probably just one more. So if you have any other questions, make sure that you let me know.